Okay, good morning. Let's get started. Hopefully you are carrying on with your final project and making progress on your weekly deliverables leading up to your final project. As promised, I'll throw out a few hints and tricks as we go to help out with some of your projects. Several of you are including randomness in your environments. I think there's a few projects where you're distributing objects randomly on the ground and trying to get the robot to go from the origin to a light source or some desired position. If you introduce randomness into the environment, that introduces an additional challenge for your evolutionary algorithm. What is it? If you'd like to evolve a robot that is able to deal with uncertainty in the environment, it's not always facing exactly the same environment, what's the added challenge you have in this case?
It needs to be more robust.
The robot needs to be more robust, right? So you're selecting for some behavior, but you want sort of average behavior. How robust is this behavior to changes in the environment? Todd?
Well, you have more variance in your fitness function, and you need an evolutionary algorithm that doesn't just kill good robots because they perform badly once.
Exactly. So you got a lot more variance and uncertainty when your system is computing the fitness of a given controller, right? You might drop a controller into the robot, it's in a particular environment, and given the situation of that certain environment, that controller gets lucky. On average, that controller will perform badly, but if you only evaluate that controller once in a random environment, it might get lucky. Or vice versa, you might drop a controller into the robot that, unbeknownst to you and unbeknownst to your evolutionary algorithm, will on average get the robot to perform pretty well, but it happens to be placed in an environment that's particularly difficult and fitness is returned as being a relatively low value. So now we have this added challenge about trying to estimate the fitness of a controller on average. What are some approaches to help with this situation?
You could run through multiple environments with a little perturbation and then average those for each robot.
Exactly, right? So the most obvious thing, like in the phototaxis task where you're evaluating every controller 4 times, maybe you make 4 random environments, play your controller on your virtual robot 4 times, and take the average of the robot's ability in those 4 environments. Is 4 enough? In most cases, not, right? Again, it's possible to get lucky. So maybe 10 environments, maybe 20 environments. Now you're evaluating every controller 10 or 20 times.
You're back to excelling in one of them and doing in the others.
Exactly.
And still being sort of not a good performance.
Exactly. What else might we be able to do in this situation to relatively computationally efficiently estimate the mean ability of a controller in changing environments? So if we evaluate the same controller just twice in 2 random environments, it's possible that a bad controller gets lucky or a good controller gets unlucky. And we can rule that out by evaluating the same controller many, many times, but that's computationally inefficient. So a common technique is to use what's called frozen noise. What this means is that you're still going to have noise in your system. You're still going to be exposing controllers to random environments where the positions of the objects are maybe placed at random positions, or whatever else variation you're introducing into your environment. That's still different, but it's frozen in the sense that every controller experiences the same set of noisy environments. So the way to do that is before you start evaluating your controllers in the first generation, you create your random environments randomly, and then everyone sees the same set. So no one controller can get more lucky than another one. You're kind of leveling the playing field. Okay, it's a common technique that's useful if you're trying to estimate the mean performance of your robot in randomly varying environments. Make sense? Okay, any other questions that I can help with, PyroSim-wise? No? Yes?
Do you have two light sources? Is there a way to identify one versus the other? Is it just kind of light?
That is a good question. I don't remember. The version of PyroSim that I created, it was the closer of the two light sources that a light sensor detected. Colin Capel, who was here as a guest lecturer a few weeks back, has improved PyroSim quite a bit since I've worked on it. I don't know if that's still the case. If you send me an email, I will post a response on Blackboard about multiple light sources.
And then one other question, do you know what the value that's returned is? Because like if it's far away, it kind of has like a small number, but if it's really close, it just gets infinitely large.
Yes, so the number that's being returned really is 1 over the distance squared up to a maximum distance, I think.
Okay, I think when I accidentally put it in the same body part, it said infinity, so I figured it just like went to infinity, but...
Exactly, so if you put a light sensor on a light source, and if they're both co-located, then it's D is 0 and the value of the sensor is infinite, which causes problems for calculating fitness and so on. Any other questions? Okay, so back to Twitch Plays Robotics. We are working our way through another open issue in evolutionary robotics, which is how to scale it up. As you all know now through personal experience, it takes a long time to set up simulator, the robot, the neural network, the evolutionary algorithm, the environments, and so on and so forth. It's a long, painstaking process. Can we automate or scale this process in some way where we can create an overarching evolutionary algorithm, overarching evolutionary robotics system that makes it easier and easier for more and more people to participate by requiring or assuming less and less technical ability on the part of the participants. So we have a large number of people participating who know little to nothing about evolutionary robotics. There's different approaches to trying to solve this, and we're looking at one that my group worked on a couple of years back, and this is a project that's still ongoing in the lab, which is to stream robot simulations to Twitch, an interactive website where people can then, through chat, talk back to the robots, and we'll get into the details of that today. We spent the last part of last time setting the stage for Twitch Plays Robotics. We obviously can't, or it would be hard to scale this up if we assume that our participants were typing in fitness functions or somehow designing environments for our robots or constructing them. What is one of the few things that we can assume on the part of our participants is that everyone more or less speaks English. Wouldn't it be great if we could allow the robots and the participants to interact with one another through normal English speech, right? Very difficult because, as you know, your robots in PyroSim don't speak English. They don't speak any human language. How can we possibly get them started on understanding language? This is a notoriously difficult problem in AI, as we talked about last time. From the point of view of a machine, English or any other human language is basically like hieroglyphics, and the best thing that an AI or a robot has available at hand is a hieroglyph to hieroglyphics dictionary, right? One symbol is related to other symbols, but around and around the machine goes, and the best it can do is say this symbol is kind of like these symbols, and these two symbols are related to one another in this way, according to this symbol. It's kind of not a very satisfying description of language understanding, and it's known in the field of AI as the symbol grounding problem. The problem is, how do we enable machines to ground symbols in something other than other symbols? The other question is, of course, do humans actually do this? Maybe all we're really doing is manipulating one symbol after the other, but mounting evidence in neuroscience, as we saw last time, suggests that that may not be the case. There's mounting evidence that shows that we understand language, or at least spoken and heard language lights up the motor strip part of the human brain. There is a deep connection between language and action. What exactly that connection is still remains to be seen, but there seems to be this deep connection suggesting that humans ground the symbols of language in sensor motor experience. When you hear someone say, don't jump to conclusions, the part of your brain that's responsible for actually performing a jump or observing a jump lights up, and in some way your brain is simulating the felt experience of jumping, and that replay of the physical experience of jumping may allow you to figure out what this English idiom is if you've never heard it before. Don't jump to conclusions. All right, here's another embodied metaphor here. Don't look back in anger. Very abstract, right? You can't literally look back in anger. Why look back? What is the embodied part of this metaphor? Obviously, you're not literally looking back at something, but you're metaphorically being asked not to look back at something in some way. What is it?
We imagine the future to be ahead of us and the past to be behind us.
We imagine the future to be ahead of us and the past to be behind us. So what's implied in this metaphor is, of course, don't look back at some past event and regret it angrily. Why do we use that pair of metaphors? That the future, we look forward to things in the future, but we look back to things in the past. How is that rooted in our physical bodies?
Because we imagine the future as like movement forward, and when you move into the future, you've got like when you move into the future, the direction that you tend to move is forward.
Because of our primary sensory apparatus, which is our visual system, when you leave class at the end of class and walk to the end of the hall and you're looking at the door to the stairs at the end of the hall, interaction with that door is imminent. It's in your near future, right? You're looking forward to, and consciously or subconsciously, you're thinking about how to open the door and go down the stairs, right? If you turn around and look back as you're walking down the hall, you're seeing the classroom and where you were a few moments before. Most other cultures also associate future with forward and back with the past, because although culture's different, anatomy is the same across human cultures. What are some other embodied, yes, Scott?
Did the motor strip light up twice for two different locations? I mean, there's both travel involved and looking involved.
That's a good question. I'm not sure. I'm sure there are some brain imaging studies where they've been read embodied metaphors. It'd be interesting to go and have a look at that literature. In this case, these are actually taken from linguistic studies. So this is very different from the neuroscience studies we talked about last time. Okay, other embodied metaphors. We're all primarily English speakers in this room, so let's limit our discussion to English.
That really shook me up.
That really shook me up. That's a good one. Takes a while to start thinking of them, but once you do, there's a lot of them.
You really got to hand it to them?
You really got to hand it to them. That's a good one.
Just take it one step at a time.
Take it one step at a time. Excellent.
Swing and a miss.
Swing and a miss. Okay. You really started to get the hang of this. I'm not going to take this lying down. There's many more. You might be nervous about suggesting one. You might be tied up in knots.
Climb the learning curve.
You got to climb the learning curve.
You got to take it and run with it.
You got to take it and run with it. Exactly. Very good. Okay. Fun exercise for your friends this weekend is to play the embodied metaphor game. There are thousands of them, right? Once you start thinking about them, they're everywhere. But this often, when you think about language, you don't immediately think that language is connected with the body or action or hands or feet or steps and so on. Why this blind spot? Why do we miss this unless it's explicitly pointed out to us?
Because it seems obvious.
It seems obvious. Language and mathematics are abstract. They have nothing to do with this dirty thing called the body. The body's just always in the way. It's not important. Where have we heard this before?
Descartes.
Descartes, right? Cartesian dualism at work again, right? Language and math are some of the greatest achievements of humankind, and they have to do with the brain or the mind or the soul, pick your term. They have nothing to do with the body. Modern science is starting to say otherwise. Okay. There's evidence that suggests there is this connection in humans, but again, the details of this connection is not clear. What does this matter for robots? Well, let's try and use this idea to allow robots to similarly ground the symbols of language in their sensor-motor experiences. So, how might this work? How could we actually teach a machine to ground symbols? Imagine we have a robot and we issue the following command to the robot, JUMP. Remember, proximal perspective. Put yourself in the shoes of the robot. The robot speaks no English whatsoever or any human language. So all the robot hears is JUMP. Doesn't know what JUMP means. How might this robot go about learning what JUMP means? Robots are equipped with sensors and motors. Imagine the robot has pressure sensors in the soles of its feet, and it's moving while periodically it hears different human words, like JUMP. And the robot senses a correlation between the symbol JUMP, or the symbols JUMP, and a particular sensory signature. Every time the pressure on both soles of its feet, let's assume we're dealing with a biped, the moment pressure goes to 0, it hears from out there the term JUMP. So the robot starts to learn there is a correlation between these two things. What JUMP means is temporary lack of pressure on the soles of the feet. That's what it means. Assume that we could teach the robot that. Then we would have at least one symbol grounded in the robot, or the robot would ground one symbol in its own sensor-motor experience. You can also start to imagine similar situations for other motoric words. So a motoric word, as you can imagine, is very motoric. It stimulates the motor strip. There's a one-to-one connection between that word and a particular part of the anatomy or a very specific action, right? Run, stop, sit still, turn left, turn right. If the robot has the right set of sensors, even a simple robot, it might be able to learn a relationship between sensor-motor experience and that motoric word. If we could teach a robot to do that, could we recursify this algorithm and enable the robot to gradually ground slightly less motoric words in more motoric words that it's already grounded in sensor-motor experience? So let's take the slightly less motoric word, movement. Maybe the robot learns that that word, or that symbol, tends to pop up whenever it JUMPs or RUNs or turns left or turns right, that there is a wider range of things that happen that cause this symbol to appear out there somewhere, which is probably a human saying, that's a type of movement, that's a type of movement, that's a type of movement. So the robot might, in theory, be able to ground the slightly more abstract word movement in as a container term for a bunch of other symbols. Right? Stop, halt, sit still, don't do that anymore. Those motoric words might similarly start to be combined together in a slightly less motoric word like cease, or no, or null, or zero. Okay. You can keep playing this game. Political movement is now more abstract again. Could it ground political movement in movement up to something very abstract like a particular type of political movement? This is all hypothetical. Whether this could actually happen, this is a hypothesis. It seems like quite a stretch, right? These very abstract words at the top here, how would this actually work? Let's take, instead of socialism, and switch to democracy for a moment. Democracy sounds like about as far from a motoric word as you can possibly get. Right? Seems obvious. Like the embodied metaphor game, can you think of some sort of motoric association that might crop up when someone is learning about the word democracy? Vote. Vote is also abstract. You could go somewhere and actually raise your hand or cast a vote. Yep. Thumbs up, thumbs down. Okay. Run. Okay. Run for office. There's another embodied metaphor. So there's a bunch of candidates out there which collectively might allow a human or a robot to eventually ground even a very abstract word in a series of more motoric words. My favorite one for democracy is tug of war. Have you ever played tug of war? It's a pretty embodied metaphor for democracy. Okay, that's the idea. Could we actually do this? That's what led to the Twitch Plays Robotics project, which was developed to see whether we could evolve robots where they evolve to ground English words in sensory-motor experience. And then, if we can, how many words, in what way, and which words are they able to ground in sensory-motor experience? Okay, I'll show you the video first. This is an ongoing project for the last 2 or 3 years. This is version 1. If you Google Twitch Plays Robotics, you can play the current version that's up there on the web. As you can see here, we're going to stream a robot simulation from our server to a Twitch channel. For those of you that have never visited the Twitch website, it's quite an experience. About 50 million unique visitors a day. Most people are streaming themselves playing a video game. Other people observe them playing the video game and type in chat as they're playing the game. If you go to the Twitch Plays Robotics channel, instead of seeing a video game, you see something that looks somewhat like a video game. We tell people that arrive at the Twitch Plays Robotics website to think of these robots as pets. These pets are capable of learning and obeying certain commands, but most of the commands you might be able to think of, they probably can't learn. And the game is we don't know which is which. Which commands can be taught to these robot pets, and can you figure out how to do so? So people on chat have 2 possibilities available to them. They can type in a candidate command that they would like to try and teach to the robot. At this point in time, 13 participants have voted that in a few seconds' time, they're going to try and teach, they want to try and teach the robot crawl forward. Someone else has gotten tired of the current robot and wants something else. Someone else is confused about what this website is. As usual, you get all of the above on the web. So there's a lot of noise in this system, as you can imagine. At the moment, let me start up the video here so you can see this going. We have the quadruped robot here. You can see people starting to vote for what they want to try and teach the robot. In 16 seconds' time, the most voted on command is going to be sent to the robots, and the robots are going to quote unquote hear the command. And we'll talk about how they hear commands in a moment. Okay, so now the purple quadruped has heard the term walk forward, and we'll see if anyone votes yes or no. If someone types in VY, that means the violet robot, yes, it's moving forward. You can see votes for VN, no, the violet robot is not obeying the command, walk forward. Now we have a blue quadruped. What do you think the change in color represents?
New controller.
A new controller, exactly, which we don't explain to the crowd. Explaining a controller is difficult, so the change in color is there to say it's kind of a new brain or a new robot. This one is also maybe or not obeying the command. So far, so good? Okay. Okay, I'll speed things up a little bit so you get the idea of how this works. We've got two different robots in here, the quadruped and the worm. They have different sensor motor complements, and you can see people voting on different commands to try and teach the robots. And for each command that the robot hears, they're providing positive reinforcement or negative reinforcement. Okay. What kinds of commands do you think the crowd tried to teach the robots? You saw a few hints there. Do a barrel roll, yes. Every internet meme you can think of at that time, 2016, it showed up. So without being told specifically what motoric words are, instinctually the crowd tended to converge on short motoric words, not walk forward, then turn around 3 times, then lie down, and then come back to the origin. That is a complex but still motoric word phrase. It was very short things like walk, run, turn left, turn right, crawl, stop, and so on, which is good news. That was our first good news from this experiment, which is kind of what we were hoping for. What else do you think the robots were taught by the crowd, or the crowd attempted to teach the robots?
Swear words.
Swear words, absolutely, right? If you have a friend who doesn't speak English, what are the first few words you tend to teach your friend? Swear words. These robots are excellent at swear words. Okay. Are swear words motoric? Some yes, some no. We'll leave that one for a discussion at another time. Okay, I will show you some of the actual commands. Some of the other ones actually were kind of interesting. One was look at the camera, right? So we put these eyes on the robot so that it was easy to infer forward and back and left and right from the point of view of the robot. Could the robot obey look at the camera, given what you know about pyrosim? Does that seem something that's groundable? Not quite, right? The virtual camera in pyrosim is not a physical object, right? But there may be a set of joint angles that cause the robot to turn so that the eyes are pointing at the screen. So maybe, yes, maybe look at the camera is groundable, possibly. One of my other favorites was be yourself. Someone else challenged the robot to prove Fermat's last theorem. Very abstract, but maybe groundable somehow. Who knows, right? Okay, so there's actually a lot of moving pieces to this experiment. So we're going to break this down into 4 phases. Act, observe, learn, and predict. You saw the first phase of this experiment where the robots are basically acting. In this first version of Twitch Plays Robotics, there was no evolutionary process occurring at this point. We were simply dropping one random controller into the robots one after the other, which would cause the robots to start moving in simulation. We captured the simulation from the screen and streamed that live to Twitch. And we used the Twitch API to then capture the chat from the crowd and then store that in a database. So as the experiment ran, we had a growing number of random controllers. And associated with each controller was the command that the robot had been issued at that time, and whether or not the crowd gave thumbs up or thumbs down, which gave us the following data set. So as I mentioned, we had 2 robots, the worm robot R sub 0 and the quadrupedal robot R sub 1. So we have 2 different robots. For each robot, it heard a series of commands C. So any command Cij, that was the jth command issued to the ith robot. So C02 would be the 3rd command issued to the worm robot. So far, so good? Okay. Several commands were issued many times. So some commands, when issued to the robot, there was more than one random controller that was executed on the robot during that command. N stands for controller. So now Nijk represents the kth controller executed on the ith robot when it heard the jth command. So far, so good? Okay. Finally, for each controller, Nijk, it may have collected 0 or more upvotes from the crowd. Yes, that controller, the kth controller, is causing the ith robot to obey the jth command. And the same controller may have collected 0 or more no votes. No, that robot is disobeying the jth command when running the kth controller. So Sijk0 is a single number, a single integer, positive integer. How many no votes did that controller collect? Sijk1, how many positive votes did that controller collect? Okay, so that's the database that we collected, the data set that we collected during this first phase. We then observed the data set before we moved on to the next phase. So in this first phase, over a couple of days, we had 424 people who played Twitch Plays Robotics. There were over 57,000 evaluations. So an evaluation was a 30-second period during which one random controller was in charge of the robot. So 57,000 evaluations. As you can imagine, most of those didn't receive any reinforcement. It was 3 o'clock in the morning Eastern time, which tends to be pretty quiet. But over 6,000 controllers, over 6,000, sorry, not 6,000 controllers, over 6,000 evaluations received some reinforcement. We got a total of over 16,000 pieces of chat typed in by participants. Any given piece of chat could be an issued command. It could be a positive reinforcement, a negative reinforcement, or the participants just chatting with one another. The crowd issued almost 9,000 commands, but as you can imagine, a lot of them were the same command, so there were only 266 unique commands, and these were the top 5 that were issued. So jump was issued 385 times, walk forward 58 times, and so on. What's common across the top 5 or the most popular 5 commands?
They all involve displacement.
They all involve displacement. They're all short and very motoric, right? If the most popular command was prove Fermat's last theorem, we'd probably be in trouble. Okay, so it looks promising. Given the sensor complement that's available in PyroSim, maybe some of these are actually learnable by these robots by detecting relationships between sensory signatures and these symbols. The crowd also typed in 7,500 reinforcements, yeses and nos. On average, any one evaluation received 0 yes and no votes. A vast majority received just 1 yes or 1 no. Some received a small handful of yeses and a couple of nos, and so on. Each subject that participated, a lot of people typed in 1 or a few reinforcements and left. Some people typed in a dozen commands and then left. There was a small fraction of people that spent 14 hours at a go on this and issued thousands of reinforcements. So we had a small but important power user base here. Okay. This last statistic here, O, this is the proportion of positive reinforcement. So if we take all the yeses and nos and look at the ratio, 0 would have been everyone typed in no regardless of what the robots were doing. An O of 1 would have been everybody typed in yes regardless of what the robots were doing. What does this value of O tell us about the general behavior of the crowd?
Very critical.
Very critical, right? So most of the votes were no. Nothing here yet tells us whether the crowd was honest or not. This is the average internet user. Are they going to be honest or not? You can go back and watch the video and judge for yourself. Okay. Okay, let's push. So we're observing the data set now. Now, after the fact, after we've collected all these random controllers, after the fact, at least in version 1, can we now train these robots to learn or ground some of these commands? The way we did this was to collect just a small subset, of all of the reinforcement we got. We went through all of the commands, and we pulled out just those we pulled out the most popular command, which was jump. We then went back through all the evaluations and filtered out all the evaluations during which jump was issued to the robots. And we then further filtered those evaluations. We threw away any evaluation that received no reinforcement. There's nothing we can learn from that particular evaluation because the crowd said nothing. So we were left with a subset of evaluations. We played back each of those evaluations, and for each evaluation, the robot heard the command jump and received at least one piece of reinforcement. It might have been one yes, one no. It could have been 3 yeses and 1 no for the same evaluation. We have at least one piece of reinforcement. We played back each of those evaluations on its respective robot and created the binary matrix that you see here. Each row in the matrix corresponds to one time step in the simulator during that evaluation. And each column represents one part of the robot's body that contains a touch sensor. The value at any element in this matrix, 0 represents that body part. 0 represents that body part was not in contact with the ground. A 1 represents that that body part was in contact with the ground. So we evaluate a robot which gives us back a subset of sensor data. And associated with that matrix, which I think is on the next slide, we can then associate with each one of those matrices, and we have one matrix for each evaluation. We can associate with it normalized reinforcement. This is OIJK. So OIJK represents the normalized reinforcement of the kth controller running under the jth command. We only have one command, which is jump, on the ith robot, the worm or the quadruped. We normalize it by summing the total amount of positive and negative reinforcement that was collected for that evaluation. And the numerator, we take the difference between positive reinforcement and negative reinforcement. So for any given evaluation, if O is -1, that means unanimous negative reinforcement. Everyone gave a thumbs down for that evaluation. Could have been 1 thumbs down, 3 thumbs down, 13 thumbs down, doesn't matter. An O of 1 means unanimous positive reinforcement. What does an O of 0 represent? An even split, right? Remember that for these evaluations, there's at least one reinforcement. So an O of 0 means there was 1 up, 1 down, 2 up, 2 down, 3 up, 3 down. Okay. Is there any relationship between these matrices and normalized reinforcement for the command jump on these robots? That was the first thing we wanted to look at. And it turns out there is. Not much, but there's a little bit. So this is all done by hand. We haven't done any training yet. We're just taking the raw data. Each green dot here represents one controller that was played on the worm, just the worm robot, under the command jump. We took the sensor matrix that we had, and we applied a function to it that pulled out a single value between 0 and 1, which represented the proportion of time that the robot was grounded. What was that function? If you have this raw matrix with touch values in it, how would you compute the proportion of time that the robot spent on the ground?
The touch sensors just give a 1 if they're touching the ground, right?
If an element ij in the matrix represents that body part, the jth body part, was in contact with the ground at the ith time step.
So the sum of j over the total I.
Close, not quite. Think about a given row in this matrix. What does that row tell you about the state of the robot at that time? Remember, each row corresponds to one time step in the simulator.
Would it have to be the number of rows with, if it's grounded, the number of rows with all zeros?
The number of rows with all zeros, if you sum the number of rows with all zeros, that's the proportion of time that the robot is ungrounded, off the ground. 1 minus that is the proportion of time that the robot spent on the ground, right? So it's all by hand at the moment. We're not doing any learning or evolving at the moment. Okay, so points that lie to the right means that the robot spent most of the time on the ground, and the further to the left a point is, the more time that the robot's entire body was off the ground. The vertical position of a given point is O, this value that ranges between -1 and +1. Okay. As you can see, that gives us the following scatter plot for several hundred random controllers that will run on the worm robot for the command jump. If you then do the simplest possible form of learning you can, which is linear regression, you get the dotted line. So imagine I give you this scatter plot and I give you a straight line, and you have to place that straight line in the plane. So that straight line is as close to all the dots on average as possible. You get this dotted line. How good is the fit? Not so good, right? It's very difficult to find any straight line that will get very close to all these points. So the robot has a bit of a challenge ahead of it. It turns out, though, and it takes a little bit of squinting to look at this, there definitely is an inverse correlation between proportion of time on the ground and the amount of thumbs up. The more time that the robot spends on the ground out here, the more unanimous no votes that the robot gets. The less time that the robot spends on the ground compared to down here, the more thumbs up it tends to get.
You're not actually using linear regression in the evolutionary algorithm, though, right?
There's no evolutionary algorithm yet. We're just taking the raw data and we're doing the simplest possible thing we could think of, which is linear regression. Let's just see if there's any material here at all for the robot to learn before we even try. Okay, so given this slope, is that what you would expect to see? So the crowd is, on average, being honest, more or less. There's a lot of noise in this data, as you would expect.
So, I mean, just in terms of like relating it to like a parent raising a child, it does seem infinitely harder to have like 10,000 parents giving you cross signals. So.
Exactly. Our poor robots here don't just have 2 parents that disagree in teaching the robot. You've got 10,000 or at least a couple hundred in this case. You can go back and watch the videos and actually watch the raw feed of people typing in commands to the robot. And yes, they disagree some of the time, but a surprising amount of the time, at least surprising from my point of view, the crowd was unanimous and honest. If the robot was clearly jumping and there was more than one person observing at that time, you would get more or less unanimous thumbs up. If the robot was clearly not jumping at that time, you would get unanimous negative reinforcement. Most of the time. Let's assume for the moment that the crowd is being honest, but there is some other command for which you get much less unanimous reinforcement. What might those commands be, given what I've told you so far?
Commands that involve more complex action and are more arbitrary in their completion, like move forward?
Possibly. So more complex commands, would you necessarily expect for more complex commands to get less unanimity?
Probably non-motoric, non-like simple motoric things like random things like the theorem thing.
Prove Fermat's last theorem. So if I played the video for you again, and you promised to play truthfully, and I ask you, is the robot proving Fermat's last theorem? What would you all say? Yes, okay, maybe we would have some disagreement.
Or be yourself.
Be yourself, that one's a little bit tricky, right? So there are some for which you can imagine yes or no. Move turns out to have a lot of disagreement in it, which is odd because move sounds like a pretty short motoric term. Why is motoric more ambiguous than jump? These two lines here, remember, represent a lot of unanimous votes. 1 or 2 or 3 unanimous yeses or unanimous nos. Why is move ambiguous?
Because jump and move forward and walk backwards all imply direction, but move in general doesn't. So people have disagreeing opinions on what move can be.
People have differing disagreements about what move means. You get a lot of robots that kind of twitch or move on the spot, and then other robots that actually displace. They move away from the origin. So does move mean displace, or does it mean just wiggle, do anything? And if you go back and look at the raw chat logs, you actually see people getting involved in discussions about exactly what that should be, and you start to see the establishment of social norms. There are periods during the experiment when everyone in chat said, all right, let's all agree that if the robot moves away, that's move, but if it stays where it is, that's not move. Right? So that's kind of interesting because it suggests the way in which words may be grounded is not just psychological, but social as well. People need to decide collectively how to ground the symbol, and then they may or may not be able to do so.
So did you get a paper on the social dynamic out of this as well?
Not yet, but we're working on it.
Okay.
We're working on it. Okay, it's an ongoing project. Okay. The negative slope to our linearly regressed line here, although it's not a great fit, it's pretty robust. So that slope, you can trust that slope more or less. What about the other robot? Here's the legged robot. Also, all commands, all jump commands that were issued to the legged robot that received 1 or more reinforcements. What happened in this case when we linearly regressed this data? Doesn't look like there's much of a correlation. Again, we have some sort of fit. It's pretty messy. Got more or less the same negative slope. Do these two robots understand jump in the same way? If you were to ask any one of these robots what JUMP means, at this point the robot would give you back this dotted line. The more time I spend on the ground, the more of these things I get. That's the robot's understanding of what JUMP means at this point. Do these two robots understand jump in the same way? See a couple of nods.
Are these the robot's only sensors? Could it be measuring other things like, I don't know, what it sees or the angles of its arms?
Absolutely, right? We could put more sensors on the robot and that might help it ground this motoric word. At the moment, we're trying to keep things really simple. Can these robots ground the symbols using just touch information, and touch information that's collapsed down to a single number, proportion of time spent on the ground? Obviously, we're cheating a little bit. We're giving some pretty strong hints to see if there's a signal at all. So the robots, you could sort of argue either way. They kind of understand this in the same way. More time on the ground means more no votes. Less time on the ground means more positive votes. But the y-intercept of these two dotted lines is different. So assuming that we can trust this line, and maybe we can't, maybe the data is too noisy, they understand this word slightly differently. Why might that be cause for concern? Who cares? Does it matter if robots with slightly different morphology ground motoric words in slightly different ways?
I mean, for this example, it might not matter, but if the nuance in how a robot understands a command leads to it doing something catastrophically wrong, then it might make a difference?
Possibly.
I think this is somewhat essential because it would robots with different morphologies have to do different things to execute the same command.
Exactly, right? So they have different morphologies, and by necessity, they're going to be able to respond to that command in different ways. We obviously don't know in detail how humans ground the motoric word jump, but at a very high level, all three of us, these two robots and humans, understand jump in more or less the same way. The more time I spend on the ground, the less like jumping that actually is. So not only do the robots have a bit of grounding of just this one symbol, but it matches more or less what a human would self-report as jumping. We have common ground. We seem to be grounding this symbol in the same way. Among the two robots, there are slight differences. Among the robots and us, there might be a bit of a difference. What happens if you have the robot twitching so that it's leaving the ground for 50% of the time, but that period is so short that it's very difficult for the humans to see? You'd get a proportion of time on the ground which is very small, but you'd maybe get disagreement or negative votes. Hard to say, right?
What if you had a robot that was galloping, for example? Would that be jumping?
I don't know, right? Let's show galloping robots to the Twitch community and see what they say. So in the course of this project, it led us to a second hypothesis. The first hypothesis is, can robots ground motoric words in their sensor motor experience? The second hypothesis, which started to arise when we looked at this data, is, do robots ground symbols in the same way? Which then led us to the third hypothesis. Do they ground it in the same way as humans? Might there be a distance metric between different groundings? How differently do machines and organisms ground the symbols of language? That is now an open problem in the field for which we don't have a good answer, but kind of an interesting thing to think about. Okay, let's come back to this specific example. We've now had our robots act. We've generated this data set, which we've observed and analyzed a little bit. We've done a little bit of learning. We've learned or regressed this line, which suggests maybe there's a relationship there that could be learned. So now we're going to do a little bit of machine learning. Remember that we have for every reinforced evaluation under the command jump, we have a matrix and a single number O. We're going to take a neural network now. This is not a neural network that's controlling the robot. This is a neural network that is going to take at its input layer each row from the touch matrix, one row after the other. We're going to push a touch matrix through this neural network. It's pretty simple. We just have 3 inputs and 1 output that has a recurrent connection. And after we've pushed through an entire matrix, we're going to observe the value at the single output neuron, which in this cartoon example here, represented by O prime. So we're going to differentiate it from O. We get a value of 0.5 at the output layer, and we're going to compare it to the actual value of O for that matrix. In this cartoon example here, or sorry, minus 0.8. In this case, there was mostly no votes, or pretty close to -1. So whatever the robot was doing in that case, the crowd said, most of the crowd said that's not jumping. The neural network, however, outputs O prime, which is a prediction. This neural network says, given this action of the robot, I think O is actually going to be positive 0.5. I think there's going to be many more yes votes than no votes. So the neural network in this case did not do a very good job. We have a big difference between O and O prime. We record that difference, take the same neural network, and now push through the second touch matrix that we have. Take this second O prime value, read it out of the output value, compare it to the second actual O value, and get that second difference. We now have 2 differences. And we push through all of the touch matrices that we have, and we have this long list of differences. We take that long list of differences and average it. So we have an average difference for this single neural network, what does that average difference represent? What does it tell us about this particular neural network?
Fitness?
It's going to, as you can imagine, it's going to be fitness, but what does it represent?
How well it was rated by votes for that command.
How, not quite, not how well it was voted.
How well it matched the vote.
How well it matched the votes, right? We're seeing how close the O primes are, which are the predictions of this neural network, how close the O primes are to O, the actual votes we collected from the crowd. If there is a large difference on average between the O primes and the O, what does that represent? We have a neural network that produces O primes that are very far from the O's. What does that mean?
It didn't understand.
It didn't understand what? What's the it here? The robot? This neural network, right? The robots were just performing random actions. The robots in this experiment know nothing. This neural network, right, if the difference is great, it didn't understand or it wasn't able to predict what the crowd actually did in terms of reinforcement. If we have another neural network, a different neural network with different weights that produces O primes that are very close to the actual O's, what does that neural network tell us? What is that neural network capable of? Predicting the crowd response, right? So what this neural network is trying to do is not control the movement of a robot. It is trying to see whether it can predict crowd behavior. Given the command, and we're just training this neural network for one command at the moment, can it predict what the crowd will do when the robot is issued the command jump, and given what the robot actually did in terms of just its touch sensor data? Why do we have the recurrent connection in here? We're pushing through this matrix of touch values one row at a time, where each row corresponds to one time step in the simulator.
Memory?
It's memory, right? So as we're pushing this matrix through, obviously the row before that had been pushed through previously is lost, except unless we have this recurrent connection. It might be able to retain or hold on to some of the information from those previous rows. Right? This is a very, very simple neural network. We could create a much larger, more complex neural network and probably get it to do a better job. Again, we wanted to keep everything simple here. So we took this neural network, which contains 4 synaptic weights, which gives us a vector with 4 values in it, the 4 synaptic weights. We create a population initially of 4 element vectors, compute the ability of all of those neural networks in the population to predict the crowd. As you can imagine, most of them are terrible at doing so for random neural networks. Apply an evolutionary algorithm in this case, and off we go. In this case, we know exactly what values we want to be arriving at the output layer, so we don't necessarily need to use an evolutionary algorithm in this case. We could have used something else, but we know evolutionary algorithms in my group. That's what we used in this case. Kept things pretty simple. Okay, so assuming that this works, how do we actually know whether this neural network has learned anything or not at the end? Hopefully the difference between O prime and O is going down, but is it really learning to predict crowd behavior given just touch information? How would we know? For the machine learning students in the room, how do we know?
Do a test. Put that robot back out to Twitch and see if it could accurately predict a new crowd, evaluating its movement.
Let's take, among our evolved neural networks, let's take the one with highest fitness, which corresponds to the one with smallest difference between O prime and O, the one that's the most accurate at predicting. And we're going to test it now. So we're going to take our best neural network, and in this case, we actually held out some of the data. So during training, we didn't actually use all the touch matrices that we collected for jump. We held out a small subset of the data, which is called the test data. The neural networks during training never saw that held out data. We took the best neural network at the end, and now we pushed through one of these touch matrices that had never been seen during training. And we get, at the output, after pushing through one of these matrices, we get a single value, which is O prime. The neural network is now finally predicting what the crowd, how the crowd will respond to that action. And if that prediction is close to what the crowd actually did, which the neural network never saw before, it's learning. Okay, so let's actually look at this data. As you can see on the horizontal axis here, we have two clusters, one for the simple worm robot and one for the complex legged robot. The green corresponds to the average performance of the neural networks that I just described to you. We train them on the touch matrices and then expose them, take the best one and expose it to unseen data. And we then repeat that whole process again. We retrain another neural network, expose it to the test data, see how well it does, do it again, again, and again, and that gives us average error. So when we train these neural networks on a subset of the data and then expose the best one at the end to an unseen subset of the data, what's the error? What's the average difference between O prime and O? And it turns out that the error is 0.42. What does 0.42 mean? I have absolutely no idea. So we did two control experiments, the blue and the red one. Okay, and these control experiments were designed so that everything was the same to what I just described to you, but we removed one element. In the case of blue, we took all of the O values for training and test, and we set them to a random value between -1 and 1. So we threw away all the actual crowd votes, and we replaced them with random yeses and nos. And we tried to get the neural network to learn to predict those random O values from the touch matrix. There is no information left among the O values. We know there's no relationship between the matrices and the random values. So as you would expect, if we train neural networks, they get higher error. Now, higher by how much? It's hard to say, but it turns out that the difference is significant. There is significantly higher error among neural networks trained on random data than it is on the neural networks trained on data from the crowd. So what that tells us is that these neural networks, even though they're very simple, they can actually learn to predict how the crowd will respond to the simple command jump. It's not great, it's not zero, but it's definitely better than random. There is something there that can be learned. Right? Kind of like our linearly regressed line. It wasn't great, but suggests there's a bit of signal in all this noise. The red control is also similar. We took all the matrices and all the O's, all the actual reinforcement, and we took the O from one matrix and the O from another matrix, and we swapped them. We moved them around. Why did we do that control? How is that different from just randomly setting all the O values? So we permuted all the O's. So when we trained the red neural networks, they were being trained on all the matrices and all the actual O's that we got from the crowd, but any given O is now matched up with the wrong or a different touch matrix. Why did we perform that second control? Why wasn't the blue one enough?
It recreates the crowd response distribution, so it wasn't a normal distribution.
Exactly, right? So as you saw at the beginning of this lecture, most of the votes were negative, right? So there's a particular distribution of votes that comes from the crowd, which is preserved in this case, right? It's just permuted. But even when we permute it, those neural networks do worse than when they're given the correct O values. So the fact that green is doing better is not because it's working with an easier distribution of up and down votes. It's because the crowd responded honestly, at least some of the time. Enough for us to start to learn to predict the crowd. Okay, as I mentioned, a lot of moving pieces to this experiment. Before we talk about the implications of this work, any questions about the method itself?
So the people on Twitch didn't really get to see the robots get better and better.
They didn't, unfortunately, and they were very frustrated about that. If you go on to Twitch Plays Robotics now, the robots are actually learning, or they're evolving in real time. As people provide yes and no votes now, robots that collect a lot of no votes die off, and robots that collect more yes votes produce randomly modified copies of themselves. In this case, we did an offline version, collect data from the crowd using random controllers, and then let's just see if the crowd is honest enough that we could learn anything. And it turns out that there is. So now we're doing it in an online fashion. The robots are getting better at obeying the crowd as the crowd reinforces the robots. Other questions? Okay, so what can we do with this fact? If, for example, now that we have this trained neural network, let's go back and rerun the worm robot in Twitch, and a new controller is run on the robot. And for example, that new controller causes the robot to spend 50% of the time on the ground. That neural network can predict how the crowd will respond before the crowd responds, right? In this case, it's probably kind of difficult because we have the dotted line, this linearly regressed line. But at least if we just use this linearly regressed line rather than the neural network, for this behavior, our line, which is our model, predicts a split vote. People are going to be unsure about whether this is jump or not, but at least we can make a guess. And the fact that our neural network did okay suggests we might be able to use this to actually predict how the crowd will respond to actions the crowd has never seen before.
I'm just curious regarding the error results. Did you examine how the linear regressor performed?
That's a good question. I'm not sure, actually. I don't know if we looked at that. I don't know whether this is better or worse than linear regression. Again, it's not great. There's a lot of noise in the system, but there's something there. Okay. Okay, so why is it important that why might it be important that we now are armed with a neural network that can predict how the crowd will respond to an action before the crowd even has time to respond?
You could automate it so you don't need a crowd?
Possibly. Maybe we don't need the crowd anymore.
Could that be used as a fitness function?
What's that?
Could that be used as a fitness function?
Possibly.
Yeah, I mean, it's just speed, I guess, but so you wouldn't need a crowd, I guess, or to gauge how honest the crowd is being.
So we kind of know at this point how honest the crowd was for this situation, right? We've learned something.
Well, future crowds, you could see it for the same command if they did something like super far away from the line.
So what if it's a very unique command? What if it's a new, or what if it's a very unique controller? So imagine by chance we find a controller that gets the robot to spend this amount of time on the ground. The crowd has never seen this before. What does our linear regression line tell us in this case? We may or may not be able to trust this line, but assuming we trust this line, what does it predict about how the crowd would respond to that previously unseen action? We start here. We perform the action. We know the robot spent 40% of the time on the ground. We go up to our line, and where we intersect with that line gives us a y value that's larger than 0. What is the line telling us for this action? What's the prediction here? How's the crowd predicted to behave? More upvotes than no votes, right? And again, the line may be correct or not, but it suggests that some of the time the predictions are correct. Let's imagine that in a very future version of Twitch Plays Robotics, the command is no longer jump. The command is do the best you can under the circumstances. As promised in this course, we've spent the vast majority of the time talking about the nuts and bolts of robotics. This is the 4 minutes that we're going to spend talking about the ethics of AI. Do the best you can given the circumstances.
Isn't it already doing that?
Good question.
How do you define that?
Ah, exactly. It's a very subjective statement. Do the best you can given the circumstances. What is best? Imagine instead of our worm robot and our legged robot, we put a little virtual car inside PyroSim, and we put little virtual pedestrians on the sidewalk and little virtual pedestrians crossing the street. And we have our virtual car driving around that approaches dangerously close to some of these virtual pedestrians. What would be best here? How would the crowd be able to judge the robot did do the best it could under the circumstances or it didn't?
If it's the car to avoid the pedestrians and then try and avoid as few pedestrians as possible.
We didn't say that, right? We didn't say avoid pedestrians, avoid as many pedestrians as possible. We just said do the best you can under the circumstances. It's implied, obviously, to stay as far away from the pedestrians as you can. Does the crowd in this case know what sensors the robot has? How does the robot sense whether there are any pedestrians around? As you've seen in the case of the ray sensor in PyroSim, imagine we put a bunch of ray sensors emanating from the top of the car, and these rays are emanating out into the environment, and some of those rays actually touch the virtual pedestrians. And the car still drives forward and drives very dangerously close to one of the virtual pedestrians at a virtual 60 miles per hour. Did the robot do the best it could given the circumstances in this hypothetical situation? Assuming the crowd knows that these beams emanating from the top of the car are sensors. Yes, it did the best it could? Okay. Assuming we have a second situation, same car, same situation, but for some reason the beams never actually touched the pedestrian. And the robot drove 60 miles an hour very, very close to the pedestrian. Did the robot do the best it could given the circumstances?
Yes.
Now I see a lot more nods, right? The robot didn't see the pedestrian. It might have endangered the pedestrian, but it didn't know. It did the best it could given the circumstances.
Plus, I mean, the point in the ethics of it, the best it can, could also mean for a situation it finds that it performs better if it follows a certain path where it may hit one person, but it's going to avoid 3 people, but it's still wrong to hit that one person.
Absolutely.
You not look at it as binary.
So any discussion about autonomous vehicles usually leads to a discussion of what's known as the trolley problem, and you can go look this up if you don't know about it. It comes from moral philosophy, which is exactly about that. How can you actually weigh one human life against another? Very, very difficult thing to do. How do humans judge these situations for other humans? The law says, did the human do the best it could given what it knew under the circumstances? Could we adapt Twitch Plays Robotics to study the ethics of AI and how well robots might be able to obey trolley problems in the way that humans do? I have no idea, just food for thought. You have a quiz due tonight, and we will see you next Tuesday.